Welcome to this lesson on uncertainty and error. In this lesson we will try to develop our understanding of uncertainty and error in relation to single and multiple measurements. To start this lesson, I would expect you to know how to calculate the mean of a set of data and how to determine the range of a set of data. Hopefully these are straightforward skills from GCSE maths. Before we begin the lesson, I'd like you to take a few moments to answer these questions here on calculating the mean and calculating the range. Pause the video and restart the video when you are ready. Hopefully you had no problem arriving at these answers for each data set. To calculate the mean, of course, we simply add all of the figures together and then divide them by 6. When you're using a calculator, do make sure that you press equals after you've added them all together, but before you divide by 6. Otherwise, you may well just divide the last number by 6 and add the rest onto them if you're using a scientific calculator. For the range, it's very simply finding the difference between the largest and the smallest value within each data set. To begin with, I would like to start with something very everyday and very familiar: measuring the length of something with a ruler. The principle we must start with is that each time we measure something, there is some uncertainty in the individual readings that comprise that measurement. When measuring the length of an object with a ruler, we actually take 2 readings for a single measurement. We read where the object starts on the ruler, and we read where the object ends. For simplicity of arithmetic, we always place one end of the object on the 0 mark, and then we simply read the length from the other end. However, 2 readings have been made. The first is judging when the end of the object is lined up with 0, and the second is judging the length of the object from the reading on the ruler. In each case, there's an uncertainty in the reading equal to half a graduation on the ruler. Let's have a look at this situation here. I'll try and measure the size of this die. So I'm lining up the end of the ruler there, which I think is at the 0 mark, and then I'm going to read off here. Now my ruler here has got some extra ½ millimeter graduations, but I'm just going to take that as 1.4 or 14 millimeters. At the 0 point, I was saying that it was at 0, but I need to really put there 0 plus or minus 0.5 millimeters. And then we've got 14 here, plus or minus 0.5 millimeters. So here, at this section of the ruler that I used, there are graduations every ½ millimeter. So each reading has an error of ½ millimeter. In total, this has got a reading of 1 millimeter. So actually the width of this die could be from minus 0.5 here to 14.5 at the widest length, and at its shortest length it could be from 0.5 to 13.5. And so what we say is overall we have got a range of 14. I'm going to add that 14.0. I'm justified to do that here. 14 plus or minus 1 millimeter, and that is going to be our reading here. So in this particular case, we would say the ruler has got a precision or a resolution of ½ millimeter for those first 5 centimeters, and the uncertainty associated with any single measurement I take from that ruler is also 1 millimeter. So let's make some notes on the first 2 definitions that we've got. Now, first of all, we define resolution as the smallest detectable change an instrument can measure. In the case of the ruler that we've previously seen, it was 0.5 millimeters for the first 5 centimeters. Thereafter that, it was 1 millimeter. In the vast majority of cases, we take this as the gap between successive graduations or successive marks on the scale on the instrument. If it's a digital display, we will take that as the resolution of the unit value of the smallest decimal place. For instance, if the reading was saying 56.7, we would take the resolution to be 0.5. Just be careful here, because there are some digital displays that don't necessarily increment up in ones. They might increment up in 2s or 5s. They're very rare, but do be aware that that can happen. Why don't you pause the video for a moment and take a few notes, and then restart when you're ready. So on this slide, I would like you to take a look at each of the 4 instruments and to work out what the resolution or precision of those instruments is. Pause the video so that you can read them carefully, note down your answers, and then restart the video when you're ready. So hopefully you'll have had no problem with these answers here. The first on this rotary temperature gauge is 2 degrees, because that is the division between each of the graduations. We can see that between 60 and 80 there's a difference there of 20 degrees centigrade, and we're able to count 10 gaps, 10 graduations. So 20 degrees centigrade divided by 10 obviously gives 2 degrees centigrade. The digital balance is very straightforward at 0.1 grams. The stop clock is 0.01 seconds or 10 milliseconds. However, this is rarely the uncertainty that we get in the measurement of time, because often timing is done by hand, and therefore human reaction time becomes a factor. Human reaction time is typically about 0.2 seconds. And therefore the way to mitigate and minimize the impact of human reaction time on measurements is not to time the duration of one event, because that would lead to an uncertainty of 0.2 seconds, but to measure the time it takes for 20 repeats of the same event to happen. With that timing of 20 events, we will still have an uncertainty of 0.2 seconds, but we're able to divide both the measurement and the uncertainty by 20. And so therefore the resolution would become 0.01 seconds, in line with what the stop clock could offer if it was used automatically. Lastly, the temperature scale on the right hand side has a resolution of 2 degrees centigrade, whether that of centigrade or Fahrenheit. However, by interpolation, that is reading between the lines, we would probably be able to achieve a higher resolution on the centigrade scale, as we could use the Fahrenheit scale to aid us. 1 degree centigrade equals 1.8 Fahrenheit. There are situations when the reading on an instrument fluctuates when measurements of a supposedly static value are being taken. In this particular case, we don't take a single reading, rather we take several readings and calculate the mean. Half of the range is then taken as the uncertainty in the measurement. Now this is different to a situation where you would take several readings while changing the independent variable. This case applies where, due to some source of random error, an instrument continually fluctuates and yet all variables have been maintained constant. So here is an example where we are measuring the diameter of a wire using a screw gauge micrometer. In these sort of situations, you would always measure at least 6 places and then take a mean, because no manufacturing process, at least that schools are able to afford, is able to achieve a perfectly uniform wire. So calculating the mean is very straightforward. We of course add all the figures together and divide by 6, and we get an answer of 2.493, which we should round to the same precision and resolution as the original readings, giving here 2.50 millimeters. To find the range is again very straightforward. We take the largest value and subtract the smallest value, in this case 2.51, take away 2.48, which gives a range of 0.03 millimeters. Next we go to find the uncertainty in the measurements. I've used here the delta symbol, a large triangle, to represent uncertainty, and that is the standard notation that we are going to use. The uncertainty here is the range divided by 2, which of course gives us 0.015. Yet we should round that and give that to the same resolution as the measurements which were originally taken, which is 0.02 millimeters. Finally, we need to express our measurement or our calculation of the mean on one line, where we start obviously with the name of the variable measured. We give the mean value that we calculated. We use the plus or minus sign to indicate that there is uncertainty in our measurement. We state the uncertainty, and of course we make sure we have a unit. So here are 3 sets of data from experiments that will be similar to experiments you have done during Year 12 Physics. And we've got repeated measurements on each of these experiments. I would like you to find the mean and the uncertainty in each value and express those in the form shown at the end of the last slide, a single line with the name of the variable, the mean value, the uncertainty, and the unit. Pause the video, and when you are ready, restart the video to check your answers. Hopefully you had no trouble achieving these answers. If you did, do look back through the video to see for a little bit of extra information and explanation. I hope the video was helpful to you.